Hi everyone. Today I'm going to talk about the differences and similarities between clustered indexes and non-clustered indexes. This is one of the most important things to understand when you're performance tuning for a given workload. In this video though, I'm only going to talk about the structures because the performance tuning aspects can cover a whole other video. Just like the names of these objects are similar, so too are the internal implementations. But don't be fooled by that subtlety. The end results can have very different behavior and even place restrictions on what you can do to the table. Let's start by taking a look at what these structures are made of internally. For my very simple example here, we'll use a table that models some of the data found in a phone book. Each row has a person's first name, last name, and phone number. If the table has no indexes at all, this is called a heap, and when new values are inserted, they're added wherever there's free space and in no particular order. Using this structure, if we were looking for a specific person's phone number, we would have to check through every single row in the table, not only because there's no order to the data, but also because even if we found a match, we wouldn't know if there were more matches later on. This type of searching is called a scan, and as you can see, it's very inefficient, particularly in this case when we know there's a much better way. Table scans aren't always a bad thing, it's just that if you don't need to touch all the rows in a table, there's usually a better way to go about it. In the phone book, the entries are sorted by last name from A to Z, and if there are any duplicates of last name, they're further sorted by first name, also from A to Z. In database terminology, this is the index key, and it's an ordered list of columns and their associated sort directions. Going back to the example, there are a couple different ways to structure the data to make it more efficient to find a person's phone number. Just like the real phone book, we can take the data in the table and physically arrange it into last name, first name order. But this is not enough by itself to solve the performance problem. It would end up doing a similar type of table scan as we saw before, but this time it would know when to stop because the table data is ordered. This is where the index part of things comes into play. After the table data is put into physical order, SQL Server builds up a set of index pages that allows queries to navigate directly to the data they're interested in. This entire structure, including the base table data, is called a clustered index. When a query navigates through the clustered index tree to the base table data, this is called a clustered index seek. This is very close to the same process you would use to find a person's phone number from a physical phone book. It doesn't only have the last name, first name, phone number entries, but it also has some duplicated information that tells you about the range of last names on each page. The index pages I mentioned work in a very similar way. Since a clustered index contains the base table data itself, this is why you can only create one clustered index. It's impossible to physically arrange the same data in two different ways without having a separate structure to store that information. And this is where non-clustered indexes come in. Let's start again with the heap structure. The second way to give order to the data is to create a separate physical structure that has the same index tree like the clustered index. This time though, instead of having the base data at the bottom or leaf level of the tree, instead we have a set of pointers or references back to the base data. With this type of structure, we can use any index key order we want because the order is independent of the base table data order. This entire structure is called a non-clustered index. In this example, the base data is a heap and the references back to it are RIDs or row identifiers. These are the physical locations of the rows in the table. Since a non-clustered index is separate from the base data could exist instead as a clustered index. In that case, the references back to it aren't RIDs, but instead are the clustered index key values. Just like a clustered index scan and seek, non-clustered indexes can also have those same operations performed on them. But the data directly available may be limited because usually non-clustered indexes only include a subset of columns from the table. If values from columns not in the index are requested, the query may navigate back to the base data using the references I mentioned earlier. If the query optimizer decides that doing that is too expensive, it may fall back on scanning the base data instead of using the index. This behavior has very obvious performance implications. Non-clustered indexes being separate from the base data brings about a couple of important features. Filtered indexes only contain rows that meet a user-defined predicate, and to create these, you add a where clause to the index definition. A clustered index can't be filtered because it has to contain all the data in the table. Include columns add copies of non-key column values to the leaf level of the index tree. This means that queries using the non-clustered index won't have to incur the expense of navigating back to the base data to get those non-key column values. A clustered index, on the other hand, doesn't need include columns because all the columns are available at the leaf level of the index. Those two features only scratch the surface of the options there are when creating or maintaining an index, so I've put some links below for further reading. Some of the features and restrictions are version and even edition specific, so you'll want to go through that material in quite a bit of detail. The takeaway as far as clustered versus non-clustered goes is that the clustered index is a way of representing the base data as a whole. A non-clustered index is a physically separate structure that references the base data, and it can have a different sort order. As of making this video, the only other type of index in SQL Server that has a different physical structure is a column store index. This type of index was introduced as a non-clustered index in SQL Server 2012, and if the pre-release documentation holds up, it will also be available as a clustered index in SQL Server 2014. While this isn't directly related to the discussion about clustered versus non-clustered indexes, I want to take a short detour to talk about the two types of index-backed constraints, primary key constraints and unique key constraints. I've already written a full post about this on my blog, so I'll include a link below, and this will be brief. Constraints in general are logical database objects. The two types of constraints I mentioned create indexes behind the scenes, although SQL Server in theory is free to implement them any way it likes. By default, a primary key constraint creates a clustered index, while a unique key constraint creates a non-clustered index. They are that way partly for safety in case the table designer doesn't realize that the defaults can be changed, and partly because that's usually a pretty good starting point. The main things to remember are that these constraints and the indexes that back them are different constructs, and also that the type of indexes being created behind the scenes can be changed. For obvious reasons, this is definitely something you need to be aware of when performance tuning. Again, if you want to go a bit more in depth, you can check out the post on my blog. So I hope this clears up a lot of the confusion about clustered versus non-clustered indexes. Understanding the structures and how they work should give you a much better insight into how to improve the performance of your system's workload. If you found this video helpful, please let me know by clicking the like button and subscribe to the channel to see more videos in the future. Thanks for watching.